Now we will construct the canonical operator here. And since I have not introduced any formulas for the canonical operator, I will not only write the specific canonical operator for this case, but some reasonably general formulas, not the most general. They are not needed and they can be found in our papers anyway if anybody needs them. But just quasi-general formulas which are good for this case. So we have, let me write it here, we have Lagrangian manifold lambda gamma given by equations written here, and I write them as x is x capital of alpha psi, and p is p capital of alpha psi. The specific formulas are written there. Well, and we have a measure, the sigma, well, equal to the alpha, the psi. And, well, a general measure on the Lagrangian manifold has the form some function times the alpha, the psi. This is a general measure. For this specific measure, this sigma is equal to 1, just equal to 1. We will need this sigma in the general form, that's why I'm writing it here. So this is the density of the measure sigma in these local coordinates, and we will need it. So we have a function tau of alpha psi. Well, and for the canonical operator to be well defined on the Lagrangian manifold, we need the quantization condition. And the quantization condition reads as follows: 2 over pH integral of gamma p dx is equal to the index of gamma of modulo 4, where index of gamma, where gamma is an arbitrary closed path on our Lagrangian manifold. This is integral of the form p dx. And this is the so-called Maslov index of the curve gamma. This quantization condition should be verified for a basis of cycles on the manifold lambda. Both sides are homotopy invariant. If you deform your cycle, then, well, okay.
So you assume that the coordinates alpha psi are global, right? They're globally defined on the manifold.
They are quasi-global because if psi in fact is...
In your example, it is the case, but I mean in general. I mean, as your assumption is...
In general, the form pdx is invariantly defined on the manifold regardless of any coordinates, so this is in fact coordinate-free. If I have coordinates, I can write this in the coordinates, but I do not have specific coordinates. This is all the same, well-defined. This is just the restriction of the form pdx to the manifold, nothing else. Well, okay, so this should be verified for a basis of cycles on our manifold. As far as lambda gamma is concerned, we have only one cycle here in the base of cycles. And this cycle is a circle of radius gamma on this manifold, diffeomorphically projected onto the x plane as a circle, if gamma is greater than 0. Well, okay, and it can be computed that the Maslov index of this cycle is 0. I will not go into details here, but it can be computed that the Maslov index is 0. So we are left with this condition, and if we compute everything, then the quantization condition just is gamma is nh, where n is an integer.
So the index of gamma here, when in 2 dimensions I see what it is, but in higher dimensions, how do you define it? I mean, imagine that in 2 dimensions it's just number of the tangent,
Yes, yes.
right? And in higher dimensions, because this is
Well, this condition just means that, well, our function tau is not single valued on the manifold, of course. But under this condition, this function is single valued, which is the only thing that matters, in fact, because we do not use tau itself. We only use it in this.
yeah, no, I was more speaking about, I was thinking about the more general case, and I was asking, what is the index of gamma?
The index of gamma is the Maslov index of gamma. It is it has many definitions. One is the intersection number of gamma with the cycle of singularities on manifold. The cycle of singularities is the set of focal points where the diffeomorphity of projection is violated. But in this particular case, you can deform gamma so that it has no common point at all with the cycle of singularities, which shows that the index is 0. So here we have just 0 in our particular case, and the quantization condition is that. Well, now how the construction goes. We have this tau, and we write the universal phase function. We call this the universal phase function. This is tau of alpha psi plus p of alpha psi x minus x of alpha psi. This is a universal phase function. We call it universal because it has this very simple universal expression regardless of what the Lagrangian manifold is. This is always the same. And what we need to do here, we need to make some substitution. Alpha is alpha of x psi into this function. And then what we obtain after the substitution will be the phase function, which will be actually used in the construction of the canonical operator. What is the equation for this alpha? The equation is as follows. In this particular case, is 0. In this particular case, it is not always, if this were always this equation, that we just could eliminate this, but not always. But in this case, this is this equation. From this equation, this function depends on 3 variables. In fact, on 4 variables: 2 variables x, alpha, and psi. And from this equation, we express alpha as a function of the other variables. Well, let's see what this equation says. So we have n of psi x minus alpha n of psi minus gamma n prime of psi is 0. This is this equation. This is x of alpha psi. This is p of alpha psi, which occasionally is independent of alpha. And this equation can be rewritten as follows. Let's multiply. We have n of psi x is equal to alpha. Well, the product of n of psi by n prime of psi is 0. These vectors are orthogonal. The n of psi by n of psi is 1, unity. So this is the equation. So the solution, we have expressed alpha from this. And alpha is, as we see, n of psi x. Well, and then phi with this substitution, let us write it as of x psi is phi of alpha of x psi x and psi it is equal to the following. So we take our 2. This is n of psi x plus gamma psi. So this is the phase function which will be used in the construction of the canonical operator. Note, in most general cases, we will still have several coordinate charts covering our Lagrangian manifold. In this example, we just do with one coordinate chart, with coordinates alpha and psi. So we'll have a single expression for the whole canonical operator without any partitions of unity, without anything of this sort. So now I will write the formula for the canonical operator, which is prescribed by the general recipe. And the formula prescribed by the general recipe, as applied to this, is as follows. If we have a function A on the Lagrangian manifold, well, then the canonical operator applied to A is as follows. Here we write e to the power ip over 4, that's square root of I, over square root of 2 pi h. And here is the integral s of x psi. Here alpha of a of alpha of x psi psi. Here we have the square root of sigma and determine. Yeah, here's I just write the Jacobian. So here we have some Jacobian effect. Here we have the density of the measure, which is equal to 1. And here we have the 2 by 2 matrix P psi, 2 vectors, and we have the determinant of it. And there is some rule which I don't write out, how to choose the argument of this when we taking the square root. But in this case, everything is very simple, because this determinant is equal to 1. Naturally, P is n of psi, so P psi is n prime of psi. So we have this matrix, something like that, and the determinant is just 1. So this disappears, and we are left with just this integral. And this s of x psi is n of psi x plus nh psi, this s of x, because gamma is nh by the quantization condition. Well, now let us take a is equal to 1. Here, one can say, oh, you told us this must be C0 infinity, that's compactly supported. But in fact, it is convenient to write the general theory for compactly supported functions, but if we can apply to functions which are not compactly supported, so that's simply the better. So we take this unit amplitude, and we end up with the following integral written here. Everything is now clear, because let us take x is equal to x1, 0, for example. Yes? Well, then we have the following integral. plus n psi. Here it is the constant, so it is some constant times Jn of x1 over h. If we take x not of this form, but some x1, x2, then some change of variables again leads us to Jn of r over h, where r is the square root of x1 square and plus x2 square. So we have obtained an exact representation of the Bessel function via the Maslov canonical operator. So these new formulas, which I demonstrated in this example, have two advantages. First, in this example at least. First of all, if we used the traditional formulas, we wouldn't obtain an exact representation. There would be partitions of unity which would have killed the exactness. So we would have only modulo some power of h. Second, here we have exactly one coordinate neighborhood on our Lagrangian manifold, which covers the entire manifold. And so our expression is given by a single integral. This is because the coordinates alpha psi is natural coordinates of this Lagrangian manifold. If we were to use the coordinates of the form, say, x1, p2, or p1, x2, then, as one can imagine, you would have to use 4 coordinate charts instead of 1, 4. So you would have four charts, unnatural coordinates, partitions of unity, completely inconvenient if you are to make some real computations. On the other hand, this formula is very well suited for implementation. And the general formulas have a similar form as well. The difference is that instead of this equation, p times x minus x, we have some more complicated equation. I will write it momentarily. And the Jacobian is given by a more complicated expression, which I do not see the reason to write it here because it is not very instructive, I would say. So, but let me just explain how the phase function is constructed in the general case. So in the general case, we have some coordinates alpha on our Lagrangian manifold. Say, well, and we split the coordinates alpha into 2 groups. So one, say, will be alpha prime and alpha 2 primes. Well, in such a way that in the neighborhood of the point which is of interest to us, the alpha prime says alpha 1, alpha k, and the rank of x alpha prime is equal to k, and is equal to the rank of x alpha at some point in our neighborhood. So this is the maximal rank which we could have. Well, then we again take our universal phase function phi of alpha x equal to tau of alpha plus p of alpha x minus x of alpha, and make the substitution alpha prime is equal to some function f of alpha 2 primes and x, where this function is obtained as a solution of the following equation. Pi x minus x of alpha is 0, where pi is the left inverse of x alpha prime. here we can take an arbitrary left inverse. Of course, you can take the Moore-Penrose inverse, but well, okay. So this is the left inverse. You solve this equation, you get this function and this solution, and define S of alpha 2 prime x equal to phi with alpha prime substituted from this formula. This will be the phase function of your representation, and the representation is largely the same as was written here. The integration will be with respect to alpha 2 primes. And here we'll, instead of this simple Jacobian, we would have some more complicated Jacobian, which is, however, no difficult to compute if you and program if you use computer. Well, okay, so this is the construction of the Maslov canonical operator, given an example of the Bessel function. Well, okay, I do not see it expedient to present the general construction here because it contains some awkward formulas, and of course it is not instructive anyway. Well, instead, I would like to begin discussing the following topic, which will be continued on the second lecture. The topic is as follows. So we have defined and explained how the canonical operator is constructed in these formulas. This is, of course, good, but anyway, if you have focal points on your manifold, then you still have integral representations. These integral representations are better than the original representations in the original construction of Maslov operator, in that you have natural coordinates on Lagrangian manifolds, the coordinates, any coordinates you wish you can take, and so on, but still you have an integral, and this integral is rapidly oscillating. So you need some computational effort to compute this integral. Rapidly oscillating integrals are, I cannot say they are hard to compute because with modern computer capabilities you can compute them, say, on supercomputers or something like that. But if you intend to make your computations, say, on personal computer using Wolfram Mathematica or so on, you need somehow get rid of oscillating integrals as much as possible. Well, and in some cases, this is possible. The idea of this is as follows. Assume that your focal point is generic. Say, in the one-dimensional case, it is non-degenerate focal point. This non-degenerate focal point, as the creators of the WKB method already knows, can be the asymptotics in the neighborhood of this focal point can be described with the help of the Airy function. However, their description was as follows. They took very small neighborhood of this point, whose radius depends on the small parameter, in fact, and in this neighborhood they take the Airy function, and then they glue the representations together. In fact, even in this simple case, one can write the representation of the canonical operator via the Airy function in a neighborhood of focal point whose size is independent of the small parameter. And even in some cases, you can write the global representation of the canonical operator via the Airy function, provided that you have no other focal points, of course. In higher dimensions, there are more generic singularities of Lagrangian projection. This generic singularization can be reduced by so-called Lagrangian equivalences to the simplest form of singularities, and to each of these simplest forms, there corresponds a special function. For example, to the Airy function corresponds to a singularity known as a fold. And if we, in the dimension 2, if you take a singularity known as the cusp, then you get the Pearcey function. And the point is that if you take an appropriate change of variables, then you can reduce your canonical operator in a neighborhood of the focal point. The size of neighborhood is not dependent on the small parameter, which is very important. You can reduce your canonical operator to the expression via these special functions of distorted argument, of course. More precisely, these expressions will involve not only the special functions themselves, but also, also their derivatives up to some order. What? This is what I will be explaining in more detail at the next lecture. I plan to explain how one deals with the folds and cusps, the Airy function and the Pearcey function. So, now, if there are any questions, maybe I could answer them. Yes, I guess I finished because I know there are some minutes left, but I wouldn't. Well,
I have a small question. In old papers, I mean, in the papers of Maslow, he also got Airy functions, right? Isn't it?
Yes. Well, yes and no. First of all, the expression in Maslow's papers, in Maslow's books, the expression of a canonical operator near the focal point is always via the integral of the momentum variables.
Yeah.
This is the general expression.
Right.
If you have a simple full singularity, then of course you can express via the Airy function, and it is written somewhere in Maslow's papers.
This will be non-uniform representation.
It is not a uniform representation, only a small neighborhood of the focal points. Its size is something like h to the power of 1/3 or something like that. This is of course good, but it's not very convenient.
Here you get uniform asymptotic formulas.
But with these changes of variables, we get uniform forms which are valid in domains whose size is totally independent of the small parameters. And this is, of course, a big...
independent of small parameters.
Yes, a big... Yes.
I have another question. Actually, here you get, as you said, a nice simple formula, right? But it is based on the fact that you have a single set of coordinates that represents the whole Lagrangian manifold, right? So as you said later on in the talk, in the general case, you will nevertheless need a covering of your Lagrangian manifold, and you'll be able to treat things locally where you have these coordinates.
Yes, yes,
right?
yes.
The fact you said that the important point is that here you get a nice simple formula, right? But it comes from an assumption on the Lagrangian manifold that you're studying, right? It's not that you get it in general.
No. Well, I am not the solver of any problems which one can imagine. So, of course, if you have some problem, that you can do the best you can do. My only observation is that usually, if you are able to use arbitrary coordinates on the Lagrangian manifold rather than only x and p, then you can get better results. But of course, you can invent a problem where this doesn't help.
What I'm saying is that by choosing proper coordinates, you can simplify the solution to some extent, or the writing of the solution, because solution is going to be the same, right? Usually it's unique, so when things go well. But what I'm saying is that it's not always the case that you can find such simple coordinates.
Yes, sure.
It's a question of luck, right?
Yes, question of luck or more of cleverness, how you choose your problems.